Good afternoon, everyone. The goal of this panel is to start a discussion on interdisciplinary research and education at CCNY. And the value of interdisciplines and can the National Academy of Engineering's grand challenges. And it's not just restricted to uh, research. Uh, Business professionals today have to employ concepts from many, many areas, including ethical theory, human rights, climate change, biodiversity, and stakeholder management. And interdisciplinary teaching can help develop the skills that are needed. I really want to focus on uh, digitalization. Digital data, analytics, and machine learning are disrupting almost every industry in every country, transforming entire systems of production, management, and governance, and will accelerate innovation and scientific discovery. So, in some sense, the most straightforward example of interdisciplinary activity is incorporating computational sciences and data sciences and machine learning into all areas of science and engineering. And this is very, very evident in COVID-19. And I'll just give two very brief examples. I mean, as COVID-19 has spread quickly from China to other parts of the world, the impacts on public health, safety and security, transportation and travel, and management of critical facilities and services, all of this is generating an urgent need for new, novel, relevant, interdisciplinary research. So with that opening introductory comments, I'd like to ask Dean Couzis and Dean Perkins to give a brief introduction of themselves with an eye on the way their disciplines have changed in the last 20 years, how the role of data science and modeling has impacted their respective disciplines, and also the importance of teaming and collaboration. So, Dean Couzis, let's start with you.
Okay, thank you, Tilak. Good afternoon to everyone that is participating. So let me tell you a little bit about my background. I'm a chemical engineering trained, both undergrad and graduate work. I joined CCNY in 1994. And my area of research is in the general field of interfacial science and engineering. And over the years, it has evolved from just looking at phenomena, those interfaces, to actually using the interfaces to synthesize materials that have unique properties. And during my stay here with City College, I also had the opportunity to get involved with it. So I went on leave for a few years with a concept idea that started in the lab and eventually commercializing it, developing a pilot scale manufacturing and commercializing that idea, that original product. So during these 26 years of being in the profession, the concept of chemical engineering has definitely changed from a concept that used to be much more process oriented to something that's a lot more product and materials oriented today. And as a result of that, our interactions as a professional with a number of other disciplines, starting from the area of economics, starting in logistics and business, going to material science, chemistry, and physics, have only increased year by year. And even when I look at my interactions at City College, they have always been with people from the sciences, my colleagues from the other engineering departments, and lately, even more so with colleagues from computer science, as the volume of data that we can actually gather from certain processes and certain testing has increased, has exploded, I want to say. And so figuring out how to analyze that data and draw conclusions from it has become very challenging. And this is an area where I see incredible growth in the last few years, both in chemical engineering, but also as a cross-disciplinary area with the other engineering disciplines and the sciences. Okay, I'll let Susan continue, and then we can have more.
Yes, thank you, Dean Couzis. And Susan, please.
Sure. So good afternoon, everybody, and thank you for inviting me to be part of this series. I'm very happy to be here. So I'm the Dean of Science here at City College. In terms of my personal research interests, I am a microbiologist, a parasitologist by training. And I think in my fields, certainly we cannot ignore the massive revolution that's occurred via leaps and bounds in terms of genomic technology. So in the span of just my career as a PI, we've gone from targeting single genes and using that genetic information to look at, say, evolutionary relationships and infer patterns of descendancy or origin, whether we're talking about diseases in a sort of linear way to communities and interactions, to now we're at the point where we sequence either metagenomics, so genes from the entire representation of a community, so the human microbiome as an example, or we could be doing this in environmental samples, to just sequencing entire genomes. And it's completely revolutionized the strategies of the field. And it's also, I would say, provided and you can use the flip side, opportunities and challenges for how we train the next generation of microbiologists, just to make it in that narrow focus, because it involves so much manipulation of data. We're almost drowning in data sometimes and trying to sort out key components such as functionality that's going on in these communities. A lot of my work has involved phylogenetics, so reconstructing evolutionary relationships to understand the history and origin of disease-causing pathogens. And phylogenetics has undergone its own data revolution as well. So again, with increasing genomic data, we have to evolve new computationally complex methods to sort through, sort the signal from the noise, so to speak. And you might not expect that something like machine learning would play a role, but in fact, AI techniques have become predominant in how we develop models for inferring these algorithmic approaches. So I'm very interested in interdisciplinary research. I feel like it always, this diversity that we bring to problems that are facing us. So Tilak, you mentioned COVID, that's on everybody's mind, but we have a lot of other severe problems that face our planet, like climate change and food shortages. We could go on. And I'm a strong proponent that interdisciplinary approaches are our only ticket forward here.
Thank you, Susan. And on that point, I'll start with you, Susan, and then go back to Alex. Can you give any examples, either, especially at the national level, where interdisciplinary research in your field has actually had a big impact on society? And then Alex, I'll ask you to respond to that same question. Susan?
Sure. So, in one of my own research foci here, which is microbiome science, and I have to say, most of my lab has been looking at this outside of the human discipline, but I've been involved through some outreach programs and other things. But I think the human microbiome is a perfect example of how we've needed to adapt to an interdisciplinary approach. So we've gone in a really rapid time frame from understanding very little about the microbial community that lives in and on our bodies. And that was based for a long time, centuries, in fact, only those organisms that we could culture. Now with metagenomics, we have a much broader picture of those communities. And so it's put us at this precipice where we know that they are important. We know that it's absolutely vital in terms of our health, our immunity. It even goes into our behavior with the gut-brain axis and how these microbial players affect our moods. But just knowing the identity of those microorganisms is not sufficient. And so what it's been interesting for me to observe sort of from this casual or at least invested outsider is the rush in industry to jump on this. And I don't want to call it a bandwagon. I think there really are some important discoveries and results to be made here in terms of human health. But rushing in to make, say, probiotics and prebiotics, you can't go into a Whole Foods and not see there's a growing section of the store that is invested in this. And yet it's going to take other elements of understanding microbial, ecology, physiology, those interactions. And then surrounding that, maybe that's how I visualize it, is communicating that information to the public in a way that is going to require an understanding of psychology and sociology so that we are encouraging people to make healthy choices without scaring them and empowering them to use true scientific reasoning and resources without jumping onto the hype bandwagon, if you will. So I think, yeah, the microbiome has for many years now, as it's exploded as a field, been a great example for how we have to tie in folks that understand everything from the ecology of succession. When you take an antibiotic and it wipes out some of your flora, what is the successional pattern at which they come back? And can we manipulate that? Should we manipulate that? But then taking it to how do we build chemostats that correctly grow the communities we want and do that in a system that can't help but evolve?
Yes, thank you, Susan. I'm not a biologist at all. Never actually took a course in biology, but this whole microbiome area is just fascinating. So, Alex, coming back to you then, how have you seen, or what breakthroughs have you seen at the national or local level that relied on interdisciplinary approaches?
So the biggest one that I have seen is the administration of natural resources that has been around for quite a few years now. Natural resources in the sense of being able to manage water, for example, which by itself is a huge national need. Because when you look at the US, for example, relative to a lot of other countries, there's a considerable water stress, or there's a considerable stress on our water because of our, first of all, industrial component, but also our agricultural growth. And so being able to understand and measure the strain on our water resources is a engineering feat on one hand, but it also relies a lot on our ability to look at the contamination of those water resources, being able to analyze these remotely, so remote sensing. Can we do this from satellites? Can we do this from flying low-lying planes? How do we sense the quality of the water and the water resources that we have? And it gets even more interesting when you start linking the water with energy. The two of them are severely interrelated, simply because if you look at water usage for the purposes of generating energy, one of the things you will realize is that more than 50% of the water usage in this country goes into the thermoelectric generation of energy. Simply, it's used in the cooling towers of whether it is fossil burning fuel, fossil burning power plants or nuclear plants. So there's a thermal contamination that you have to worry about there, and being able to map it. And so that's a field where you bring into play the hydrology, you bring into play engineering, and of course, the results of that kind of thermal contamination on the local life, whether it is vegetation or whether it is actual bacterial or other forms in the water stream. But then you also have issues that have become very politicized. So for example, water usage in oil and gas extraction. And that is another huge problem in the sense that while there isn't a lot of water usage there, typically it is usage of water in very arid areas. So there's other priorities with regard to how the water is going to be used. Should it be used for extraction of oil and gas, or should it be used for other purposes? And this is where collecting data and understanding both the geographic and the temporal or the time component in the problem allows you to make decisions. And also understanding the effects of potential contamination, underground or not, plays a huge role. So recently we came across a problem where we had to understand if we were to include certain chemicals in your typical process of extracting oil and gas from the ground, what is the possibility of contamination? How does this contamination front grow? And so if you write a typical proposal to any of the agencies, these are 5-year proposals. And so you run the problem that by the time the research is done, you still haven't gotten enough time data to get an idea of how the chemistry moves underground. What's interesting here, though, is that the EPA requires that all oil fields have very detailed information of what is actually fields. And so you can go back and look at that information. And by the way, just in the US, the staggering number, there's about 2.5 million oil and natural gas wells, of which about half of them are shut down or they're not being used. But by using the information that exists and doing analysis around those wells, you can figure out the temporal component, how the material has actually moved away from the well point. So now you can collect data, toxicological data, and also transport data with regard to different molecules that then you can correlate to their structure, they can correlate to the rock formations. So just by looking at data and getting the metadata structure correct, you can extract a lot of information about a project that even though time t equals 0 is today, you've got access at 20 years worth of data in the past. And you learn about the transport, and you learn about the possibility of contamination, et cetera, from those chemicals. And that is actually very interesting because for the first time, you can start predicting what different materials will do when they're injected under different conditions, whether these are oil wells or whether they're aquifers or whatever the situation. And this is an acute problem for our country because the geopolitical, and this is the next part where I think, not talking about just sciences, but bringing in other understanding comes into the play. For example, political sciences and economics. We have a situation where the US today is considered the #1 producer of oil and gas. And that's a huge financial, political, and economic benefit for the country. But there is a side effect to all of this, and this is water usage. And it actually relates also to the price of oil. So when you start putting all of these things together, how do I decide whether I'm going to use water in one particular application or another becomes really a decision tree requirement where all the information feeds in before you can make the decision. So I think these are exciting times because we have the technology to look at all this data and analyze it, and what I call being able to slice it in different ways to come to the conclusions that you need. So that's an example that is not biologically related, that it comes out of more of the energy and water situation that we have in this country.
Thank you, Alex. I'd like to ask the participants if you have any If you have any questions or any comments, please do put them into the chat session, and we will get to them at some point. It's going to make for a much more effective discussion here if it's more than just me and Alex and Susan sort of exchanging ideas. We would really love to hear from all of you. So with that, let me get this down a little bit more to the local level. Clearly, a lot of what we are talking about here in terms of computational sciences and data sciences and machine learning, it's all characterized by huge amounts of data. And so you need to have the ability to store the data. And of course, you need high-speed computing to process the data. Right? And that's why machine learning is actually becoming so critical, because in some sense, machine learning thrives on big data. So the question is, to what extent does CCNY have the needed capabilities to really do some serious work in this area? And Alex, let me start with you.
So from the perspective of data analytics, the prime department that pushes hard on this area would be computer science, and of course the mathematics department. And there is always work that's done in places like physics, in collaboration with some of the engineering disciplines. I would argue that, and I'll wear my dean's hat, and maybe we have administrators listening, there's not enough. So given the opportunity to hire and find talent, nobody, I think, would say no to that. This is an area that contributes to many of our other areas of excellence. It allows us to crystallize a lot of the fields that we're working already on. And computer science already is doing a remarkable job, and so are the other, as I said, the other divisions. But I would argue that if we had a little bit more, it would be in even better shape. As I said, is computer science for us.
Yes. So I was maybe talking earlier. Yes, of course, we need the required skills, but I was talking more about sort of the capabilities that that CCNY or you as a dean in the college can actually get or marshal the needed storage, compute capabilities to really be able to make a difference. And I think the question I was trying to get to is, well, do you have access? It can't just be computer science, right?
No.
Do you have access to facilities that will allow you to do serious work in this area? Facilities and talent.
So there is a supercomputing structure built within CUNY. I have to admit, I'm not 100% sure what its capabilities are for the kind of analytics work that we need to do for data analysis. I'm not an expert in the field. I would, definitely let others that are have a lot more expertise in the field comment on that. But partnership with companies, in the area would allow us to extend this capability. One example is obviously IBM, or something along those lines. As I said, there is a computational center that CUNY has put together over the years, and I'm not 100% sure what its total capabilities with regard to are in data management.
Okay, so Susan, you as a user, and a researcher who was trying to solve this huge problem with understanding the microbiome. Do you feel like you have access to the right kinds of resources, data, compute, and talent to actually make a difference?
I mean, I would be remiss to say that we have everything we need and there's not room for growth. I mean, certainly there's a lot of opportunity to increase. And I guess that's maybe my take is we can grow into the capability depending on what resources we have access to, right? So we can shrink our questions a little bit if we can't, say, store hundreds of millions of genomes, we can only store a few. We'll work with those and ask slightly different questions. I was going to offer that I think, and it's not unique to science, or I could even whittle it to biology. You know, one of the challenges that I've observed for many years, I was at the American Museum of Natural History before I moved to City College this year. And I think what's challenging from universities' perspectives, and certainly from folks like Alex and myself as deans, is that computation is a highly variable thing, right? So some researchers and processes need parallelization. They need to be able to rapidly crunch numbers and get to optimization results. But some of the work we do requires much more memory capability. So if we're thinking about protein structures or visualization components, or genome assembly falls into that bucket. And so those are two different resources. And I think that is a perennial problem of institutions, is deciding how to apportion the limited resources they have to best service the community. And do we store things, or do we provide facilitated download capabilities so that we can get it back, work with it, but not have to worry about the storage? And I'll just give one slight example here, which was talking to one of the early genome researchers who's done a lot of human genomes, and you know, we don't do a lot of that at CCNY, but certainly it's being done. And in some cases, it's cheaper to resequence the human genome from the sample you've stored in a freezer than it is to store the data to go back to. And that's always stayed with me as an example of the tough decisions that we make and the levels of calculation that have to go into these priorities for an institution or a department or a lab for that matter. Yeah.
Right. So I don't think either of you quite said it this way, but let me just try to summarize what I heard. What I heard was that in this whole discovery, innovation cycle that both of you are involved with, computing, storage is absolutely critical. And at this point, you're not necessarily feeling that, hey, I can't move forward without a huge additional capabilities. Would that be a way of summarizing what I heard?
Well, I think, you know, Alex said this a little bit. I think we also form strategic partnerships that help enhance that. So we've been chasing some collaborations with the Flatiron Institute, which is all about, you know, high performance computing and offering that capability. And obviously that's something that we would love to be able to do. And then there are other ways I think that partnerships can help us out in that regard. So, you know, I guess maybe it's a parallel system to what Alex was talking about with the water. You know, we shouldn't all have top of the line high performance computing clusters if they're not going to be used all the time. We should try to find the best brokerage of shared resources so that everyone gets what they need without redundancy that we don't need to do.
Yeah.
I think Susan is absolutely correct. Universities today cannot afford to duplicate efforts that's out there. And part of us being inclusive, part of us being convergent in what we do is the university is taking a role of putting together these partnerships that if you were a company, you would do them anyway. Why do them as a university? So there is Amazon web services out there, which has probably one of the largest data storage capabilities available. There is Google out there. There is IBM out there. And I think instead of trying for a school to replicate, which is really an impossible task, let's be brutally honest about this. Instead of trying to replicate, you partner. And there's advantages to that. In the sense that now our top echelon faculty and our students will also work with top echelon engineers and scientists on the commercial side. You have access to incredible resources, working on projects that you could have an Amazon, you could have a Google be a partner, or any other company along those lines. And I think it benefits our students and our researchers because we do not have to worry about maintenance of these equipment. We don't have to worry about the maintenance of these databases. They're a tool. See, I always try to differentiate what is something worth research versus what becomes a tool for research. And the database and the data storage, at least in my mind, is a tool. And if I can find a way to use it without having to worry about its installation, its maintenance, et cetera, I'll take it. I mean, there's just no discussion about that. So I think it's also a message to our students that partnerships and collaboration are what allow you to build better teams. So an analytics person or a data scientist from these companies could be extremely powerful and extremely beneficial because we will learn from them. And we will develop as academics techniques for data analysis that they could potentially utilize. So I think it goes back into this concept that a team is stronger than its components. And I think that's part of what we have to teach the scientist and the engineer of tomorrow, that at the end of the day, you have to depend on a team to solve problems.
Yes, that's a very, very good point, Alex. I don't think CCNY should try to replicate these facilities. So it's really more about, do you have access to them? And you mentioned partnerships. And Susan, you mentioned them too, and that is the right way to go. And I think both of you are probably aware, but just for the sake of the listeners, NSF is actually very aggressively trying to, through various different programs, is trying to make the resources, whether they're high performance computing resources or whether it's cloud resources and databases available to researchers. And so NSF should also be viewed as a partner in these activities. And I guess for you, Susan, it's probably also NIH, right?
Yeah, I think, those are both really important partners. I was an NSF program officer, so I probably know that aspect a little bit better. But certainly that coordination between those agencies is vital. And, I don't want to be too political here, but, going back to the microbiome discussion, one of the most exciting things that I got to participate in, and this is going back, wow, maybe 6 or 7 years ago, was an event at the White House in the Eisenhower building that was convened, sorry, I'm searching for a word, convened by the Office of Science and Technology, because they could see that the microbiome was this burgeoning field. And so they spent a day pulling together NSF researchers, NIH researchers, NASA researchers, as well as industry partners, so that we were all on the same page so that they could define these questions. And so I do want to just also throw out there, since you mentioned NSF and NIH, that the governmental partners are an important component of this as well. We rely on them, as you just said, to fund things that individual institutions or even groups of institutions could not do on their own. So,
okay, thank you. I don't see any. I'm looking at the chat. I don't see any input from anyone, any of the participants, and I would really, once again, either all of this is absolutely correct and crystal clear, in which case that's good news. But given the complexity of the subject, I would think that there would be comments and questions. So please don't hesitate to put them into the chat. So where you left it off, Alex, let me pick up there and talk about interdisciplinary teaching and how we can sort of facilitate development of the right kinds of skills. I mean, there's all kinds of evidence that interdisciplinary teaching, as I mentioned in my opening even, really does build certain critical thinking skills and a whole bunch of other skills, ethical skills, to be able to address real problems. So how do what does CCNY do, or what does the engineering school do in terms of really interdisciplinary teaching interdisciplinary teaching?
A lot of the efforts that we do on the interdisciplinary teaching, a lot of it is done actually at the master's level. At the undergraduate level, there's a rigidness in our curriculum, and really the interdisciplinarity comes in by the ability of the students to take either technical electives or just electives in other divisions, not even within the same division. And luckily, we've got a partnership here with Sciences and the Colin Powell School as well, where our students can go and take courses that allow them to expand on their appreciation of different areas. But from a perspective of where the interdisciplinarity component comes in a very designed way, you do see it at the master's program and even at the PhD program with certain courses, where really the students take fewer courses from the mother departments and a lot more electives or combined courses, where potentially these are courses that were developed by a number of different departments to address a particular need of training a student in an interdisciplinary environment. So at the undergraduate level, it's very difficult to do that. And for however much we try, and you look at the curriculum that all the departments develop, at the end of the day, we also have to comply with accreditation requirements. And so it becomes interesting on how we're going to bring in that interdisciplinary component into basically a curriculum that's extremely tight. Okay.
Okay. I will ask you the same question, Susan, but we have something in the chat from Linda Powell. And the issue is how to develop students who can understand what questions need a multidisciplinary approach, and our discipline silos make it very hard uh, to get students to think broadly. And this is a fundamental issue in many academic environments. Would you care to comment on that, Susan? And then Alex, we'll come back to you.
Yeah, sure. And I agree with what the point that Linda made. And I think what Alex says is parallel to that. I think our curricula don't necessarily have a lot of room for some of these electives, these broadening courses. And I guess my take, and something that's come out of some conversations, say, that I've had recently with Andy Rich, who's Dean of Colin Powell, and others, is that I think one of the fundamental issues is that we don't always speak the same language. And social sciences use different terminology than sort of the hard bench scientists, et cetera. And I think that's first and foremost one of the hurdles that we need to do. And I guess my approach is evolving to say, okay, we talk about interdisciplinary master's programs. That's super ambitious, and we've done it across a couple of disciplines at CCNY. We could talk about an interdisciplinary course. Sure, we can do that, and I'm interested in that. But we could even wind it back a little bit and just say, all right, I'm teaching physical chemistry, but I'm going to bring in somebody from economics. What do those people possibly have in common? And yet I think we can build some of those bridges. I made sort of an outlandish one, but we talked about this with COVID a little bit, or danced around it, or with water. It's not a problem that you can solve with just engineering or science with the technology. There are all of these other components to it, economics and politics and psychology, et cetera. And so, maybe something that we can do, something I would love to see happen, is bring students from different disciplines together, give them a problem to solve, let them realize that they can only take their solution so far with one aspect of how they're thinking about it. And I guess, I think about our Master's in Translational Medicine program. I'm such a big fan of it because it is a program that tries to give students that full 180 or 360 degree experience. So you might develop technology, but then you can't just develop it. You need to market it. You need to take it and convince people that it's worthwhile. And so I think pushing students to those limits where they realize they can't finish the job, so to speak, without collaboration in an interdisciplinary way really underscores that, and I think illuminates to them either the skills they need to develop in themselves or the partnerships that they should form to really carry ideas through.
Okay. Now, one of the things that I have learned through my experience, mainly in industry, is that you can't leave interdisciplinary research or interdisciplinary teaching to chance. You have to have some plans. So Alex, would you like to comment on how CCNY might sort of make progress in this area?
So, yes. The key element here is to have our undergraduates, doesn't matter which division, but as you seek solutions to problems, and whether you're a natural scientist or whether you're an engineer, at some point you're going to have to ask questions that address issues of finance, ethics, legality, societal impacts, interactions with potentially other technologies. And it's the thing that we can do the best for our students, and actually Susan pointed to this, is allow them to be multilingual, not in the sense of being able to communicate not just with other engineers, but being able to communicate with a lawyer, being able to communicate with a person that does biology, if that's not their major, with economists, with historians, with uh, societal type sciences. And that is extremely important. And I think that's the grand challenge, because they have to learn a new language or multiple new languages. And how you do that, I think, is the challenge, because at the same time, you've got to be able to offer the basics. And I honestly feel that the opportunity that we have to do that is at the senior level, especially if you look at engineering, the senior capstone design course. I think that's where we treat those courses less than just an exercise in coming up with a design, but we treat them as a real commercial, I want to say, or societal problem, where you have to come up with a solution that not only works technically, it works commercially, and it works from a societal perspective. So, you have to go and ask the question, is this important to a community? Is the community ready to adopt it? And if they are going to adopt it, what's the price of adoption, on top of whether it's technically possible and financially feasible? And
Alex, you're saying that's a message to the students.
it's a message to the students, but it's also a message to the educators, in the sense
Yes,
that
absolutely.
the design course, the senior year, has to be seen as not an opportunity to plug holes of what happened or didn't happen in the previous 3 years. It is the opportunity to take everything that a student learned in 3 years and also expose them, in many ways, to this ability that they adjust to the foreign languages, the foreign language of the other disciplines. And you've got a year to do. A lot of other countries, engineering is 5 years. So you've got a little bit extra time to do that. Here we do it in 4 years. So you have to do it during, I can't see it being able to do that unless you do it at the senior capstone level. Now, there are certain majors, and it came up in the chat, that something like environmental engineering that does draw for multiple divisions. That would require a lot of our key departments and divisions to rethink a lot of how we teach. And that is not evolutionary. That's really a revolution on how we do things.
Right.
Okay.
While there was a question that came up in the chat, which I think is an important one, which is, this panel is about interdisciplinary responses to emerging challenges. So in your opinion, which are the challenges that CCNY is best suited to take on?
Well, I'm happy to jump in a little bit. I think we are a special campus in the sense that, when we are in person, I can express this in a geography, there's a medical school, there's an engineering school, we have the science buildings, we have a school of architecture in about a 4-block space. And it's not a huge campus, right? I think in many ways we are a mini version of a large major R1 institution, except we exist in a smaller community with a lot of potential. And I think some of it's unrealized potential, but definitely potential for conversations across schools and across disciplines. And so I feel like we have such a great opportunity. Again, I want to just go back to what I was saying before. I think we can start thinking small. This panel or this conversation is a perfect example of that. Like, just get deans of 2 schools having a conversation about what things they have in common, and where they could go from that. You know, it doesn't have to be as closely allied as science and engineering, which are a natural pair, but we can have these conversations across every school and campus and engage students from those disciplines so that they understand the perspectives that both students and faculty and the professionals in those fields, where they're coming from, the questions they're asking, the challenges they're facing, et cetera. So, I mean, I guess maybe I'm not answering that perfectly, but I think we're not uniquely, but specially positioned to do this in a way that a large, complicated, I'm thinking about, a major University of Michigan or one of the big schools, the med school might be across town. How would you go over and observe something in their lab? It just becomes geographically challenging. No, it's across the street. You can go to Harris, or CDI has got engineering and medical researchers and science all in the same floor. So, we are well positioned, I would say, to do it.
Yeah, and I think that's very well said, Susan. I would also throw in there that this institute that you are all part of exists within a certain community, a neighborhood, let's say, right? Which is also unique, and therefore maybe there are particular problems that are associated with the neighborhood that this institute is situated in, where you could really have an impact on society, right? And it's probably worth thinking about how to go about doing that. But Alex, let me ask you your opinion.
So I think we're positioned, our students, or at least my vision, is that our students are positioned to solve or address all societal problems. I don't want to pick favorites that we're better at this or that. My hope is that a CCNY grad has understood what it takes to understand the definition of a problem, being able to break it down into its elements, figure out how to address those problems, and then resynthesize the situation and being able to come up with a solution or a set of solutions that address it. At a minimum, they have to be able to recognize that what is the team they need to put together to address the problem. See, I think the one thing that we have to do as educators, and be very open about this, is not a singular person today, let's be honest, is going to solve a lot of these problems on their own. It is the ability of that person to, first of all, work in a team, and if possible, put the team together. The values in the people, the values in the diversity that comes by putting a team together and understanding how to communicate and how to be able to organize that team to address the problem. I think that's the future of physical sciences, that's the future of engineering, that's the future of data. Not a singular person is going to be able to do all of that. Let's be realistic. That's an impossibility, at least in my mind. The great thing is to be able to lead that team and to put that team together. So I think I'm not gonna, Tilak, I'm not gonna say that we are better suited for this or for that. What I'm hoping is that the students learn that there is value and strength in numbers that usually is bigger than just the sum of the numbers.
Yes, I think that's also very well put. And from a teaching perspective, I think it makes a huge amount of sense, Alex. But if I take that original question up to the research level, right, as opposed to the teaching level, I think there's an opportunity for the institute, for the whole CCNY community to actually pick some challenges, some real challenges in the, I don't know what better word to use other than in your neighborhood, where you can have an impact and use interdisciplinary approaches
Okay, so from that,
to get there.
oh my God, so the list is long, but it is, you know, so one of the key elements here where we can have an impact. So I'm gonna draw the concentric circles moving away from Harlem. You know, so we start off with Harlem and trying to move away from that. The key element here is providing opportunity. The first thing that City College should be able to do is provide opportunity in showing students at the high school level or the middle school level that an education in STEM matters. That's the first thing. Being able to inspire students. So I think our first role or our first mission has to be inspirational. It has to be to show the students that we make a difference. That when you go into a STEM, multidisciplinary, inclusive type major, it doesn't matter whether it's engineering, whether it is the natural sciences, but one that has this multilingual ability that I was mentioning earlier, you will make a difference. I think that's the first thing. I think a lot of our younger generation today are very worried about the path that they will select. Will it have an impact or not? And I will say, yes. I mean, that's what we have to show the local community. I think that's start off with. When you start thinking about our research and our ability and what we do within the school in engineering and what we do in sciences, and we bring in the Advanced Science Research Center and the medical school, Colin Powell, and architecture, we have the best lab in the world in the center of New York City. Which problem do you want to raise? The energy problem in a highly densely populated environment, there is no better place to study the problem. If you want to talk about the ability to come up with a city that basically is self-sustained, you know, you're talking about the interactions with the DEP, you're talking about the interactions with the sanitation services, the municipalities about dealing with wastewater treatment, et cetera, et cetera. I mean, there's just the whole concept of mining from waste for all the goodies that are in there. I think it just makes for an enormous opportunity for research in engineering, physics, chemistry, biology, hydrology, you just name it. It's just you can go the whole path down there. When you think about issues, societal issues, where engineering and science and math and data come into play, transportation. Is the mode of transportation in a city that is 10 million plus, right things the way we're doing them today? What is the transportation mode going to look like 20 years from now? Are we going to be the Jetsons? You know, is that a reality or not? So you know, I would argue that the city in itself, New York City, provides City College a unique opportunity. And we are very well equipped, but I would like to see us even more so to take advantage of the biggest urban lab that's out there. And it's called New York City.
Right. Yeah, a living lab. So I think Alex and Susan, one question that comes to me is it worth somehow picking one or two or three of the examples that you mentioned and try to make it happen?
Yeah, I think so. I mean, I have to say, you know, even though you just heard what I said about us having this great potential, it's been a little shocking to me sometimes to realize that faculty, even between departments within science, don't know each other. And so, you know, then that just exacerbates. And so I guess I say that because I think we should find more opportunities, and maybe this gets at the last question Ilana was asking, more opportunities to get our faculty together so that they hear what each other is working on, but also what they're interested in working on, what interests they have, what special skills they might apply. And as broadly as we can do that, I think organically we can make that come together. I mean, I guess I wouldn't want to say as Dean of Science to my faculty, I want you to go out and solve global warming, you know, but I would rather pull some of the faculty together in my division and across the rest of the college and say, where do we get convergences? You know, where do we, there's the word that we were going to end on, where do we get these convergences? Where do we have some mutual information? And so, I mean, that's the other thing I feel is my role as a dean is a bit of a matchmaker. You know, I did this last week or a couple of weeks ago. I said, wait, one of my faculty in math is applying really similar methods that one of the physicists is doing. It turns out they'd never met. And so I said, hey, you're both working on a similar problem and using similar skills. So I think so much of it is exposure. You know, I wish I had endless time to go see everybody's research talk so we could do more of that. But I think facilitating that, and I hope that this is a silver lining that comes out of the Zoom world in the post-pandemic, is that we don't have to physically be present in the same place. We could be collaborating within the institution. As Alex says, we are New York City. We have so many amazing institutions and industries, and sure, it's a subway ride in normal times, but now it's logging into Zoom for half an hour and hearing what folks are doing. So I hope that this pandemic has that as a good turning point that breaks down some of the geographic barriers that we have.
Thank you so much. I'm looking at the clock here and it's 4 minutes past 1. I think it's time for us to start closing this session. So I'd like each of you, Alex and Susan, to kind of make a closing statement with respect to the discussion we've been having on interdisciplinary research applied to emerging challenges. In particular, now we've talked about also emerging challenges at CCNY or in New York City or in the Harlem. So, Alex, please.
Sure. I have to take Ilona's question, you know, Professor Kretschmer from chemical engineering, the whole incentive that we can provide as deans, and Susan tried to answer the portion of that. And I'm thinking here, the luxury that we've had for the last hour of being able to talk about how we feel about interdisciplinarity, convergent research, what we care about, and being able to do this on a regular basis in an academic institution without having to worry about a lot of the other things that we're supposed to do. I think that is the starting point of talking about any other kind of collaborative, interdisciplinary, convergent, far-fetching ideas or how we address things. The thing we have to realize is that without communication and without having the ability, and this goes back also to what Susan was just saying, without spending the time to learn what your peers are doing, what your cohorts are doing, there is no chance of being able to execute on any of these things. So I would argue that part of what has to become the culture, or we have to re-energize, is the discussion, is this ability to, whether it's virtual, whether it's in place, brainstorming, good old brainstorming sessions, where we sit and we discuss, something that we read or something that's been bugging us or something that we find exciting. And who knows, maybe a great research idea or a great teaching idea might come out of all of that involves the people that you're chatting with. And so my point also to the people that are listening, especially the students, communication becomes the most important thing. What are the skill sets that you have to be able to utilize, whether it is writing a good memo or coming up and having a great discussion with a set of colleagues, and that leads to the definition of a new problem and eventually a solution to that problem. Put time on the side for what you do on a daily basis to read and to talk. And otherwise, I don't see interdisciplinarity. I don't see convergent ideas floating. They come from the people. So I'll stop with that.
Yeah,
Thank you, Alex. Susan?
I was just going to pick up on what you said and also steal something that you said yesterday, but you didn't say today, so I'm going to steal it. And that is the risk-taking aspects of it. And I think that's something too that we can do, which is reward people that come to us with ideas. And I would, in terms of interdisciplinarity, that doesn't have to come from me, or it could come from faculty. It could also come from students, right? So I was mentioning when I interviewed, I threw out a couple examples of, in this sense, courses like I work on malaria, and that's a very interdisciplinary problem, like any disease. It involves the biology of it, but also economics, architecture, political science. There's history involved in that as well. We're seeing that with COVID as well. I threw out something like photography, right? So we have chemistry, we have physics, we have the aesthetic aspects of photography, and then history as well. Social media is a great thing, which involves technology as well as psychology, network systems. Transportation was something that Alex just mentioned. You could have the engineering aspects of it, but also architecture, sustainability, I'm just throwing these out as examples. And I would love for us to develop a system where students could develop these, right? To come to us and say, here's a topic and let's pull in some faculty. And I would love to see us be able to do this outside of a rigid structure, right? We exist in semesters, and it doesn't have to be that way, right? We could start to do things in smaller chunks, either as a week-long intensive session, or just a weekend hackathon or ideathon. I forget all the, solve-a-thon, I guess, is the new buzzword for those things. I like that. And I think, this is something that I'm getting excited about, is just, forgetting about some of our traditional molds and providing our students with experiences that give them these opportunities to hear each other, and students and faculty, as well as the whole community, that are a little bit easier hurdles to jump than trying to, create a whole new major or even make a semester-long class. So it's something I hope I can start to catalyze from my standpoint as well. I get really excited when these connections get made, and you see, as Alex has iterated, my mantra as well, the sum is always much bigger than the parts, because you will take those differing perspectives and get to a place that you never would have if you just take folks with the exact same skill set and the exact same perspective. They're going to keep screwing the same screw into the same hole without asking, let's stop using screws and let's build use adhesives instead of that. So
thank you, Susan. For my part, it's been a real pleasure to have this panel discussion with two wonderful down-to-earth deans. And I also appreciate all of the comments from the participants. And my hope is that this not become like every other panel discussion that I've been on or had the pleasure to host, where, all right, I've had the panel discussion, now I'm going back to work. I hope what the two deans said in the end is something that we all sort of keep in mind, right? And try to, in whatever little way we can, try to continue this thought process and this conversation even without a specific panel discussion. So thank you all participants. Thank you, Alex and Susan. Back to you, Claude.
Thank you to the panelists and to Dr. Agerwala for a spirited discussion. We will be back here in a couple of months with more of the executive in residence. Thank you for coming and have a good afternoon.
Thank you, everyone.
Thank you.